Hello students, I am Akhilesh Kumar Srivastava from ABS Engineering College. In the series of data structure lectures, we will discuss today about the insertion sort. We already have discussed about the bubble sort and the selection sort in the previous lectures of the sorting. Today we will discuss another sorting technique, which is a order of n square sorting technique. Bubble, selection and insertion sorts, all these are the brute force approach sorting techniques, wherein the effort required is order of n square. So, the outline of today's lecture will be seeing what the insertion sort is, how we perform the insertion sort. Then we will see the analysis of the bubble sort, we will see the analysis of the selection sort, and then we will make a comparison between insertion, selection and the bubble sort, and we will find out which among these three is the best one. So, let us understand the sorting first. Let us say there is a table, and in this table, let us say there is a table, and in this table there are many elements. There are many records here. Each of these records are randomly written, randomly arranged. With respect to every record, there are various fields, but in this field, one of the field is selected as the key. This key will have the unique value. Unique means it cannot be duplicated. For example, if this is the student's roll number, it cannot be duplicated. Every student will have a unique roll number. An employee ID or in any organization, that will also be unique. So, the Aadhaar number, for example, that is unique. So, that is the key value. Now, we need to arrange these records according to the key values, then we will require the sorting. Let us understand the insertion sort. What happens in the insertion sort? We will consider that we have an array which contains the elements. We will divide this array into two parts. One of the part will contain the sorted elements, and the another part will have the unsorted elements. We will pick one element from the unsorted element at a time and will insert that in the sorted part. So, every time one element will be taken from this unsorted part and that will be inserted in the sorted part. So, this is done one by one. Now, let us say we have this array 10, 20, 30, 40 and 15. In this you can see that this part is sorted and the unsorted part contains only one element, that is 15. In case we have to insert this 15 in the upper part, which is having the sorted elements, then you will first have to find out the position of the element. It means where in this array should this element be inserted. So, the first operation will be finding the position where it should be inserted. So, we will have to perform the search, and then once you have found the position where it should be inserted, you will have to insert this element. For example, when you will find this position, this will be the position where this element needs to be inserted. Now, if you have found the position, this element will be inserted here, requiring that all the elements should be shifted one step below. It means if you have to insert this 15, before the insertion, the element 20 should come here, element 30 should come here, and element 40 should come here. So, at a time you will be shifting only one element at a time. Okay. The insertion process has also been explained, which says that the last element should be shifted first, and then the second last element should be shifted, and then the third last element should be shifted, and so on and so forth. And finally, when you have a place for insertion of 15, 15 can be inserted here. So, the two-step process is required here. One is that you find out or search the space where it should be inserted, and the second thing is that you insert the element, requiring that the elements should be shifted one step below. Now, there are two operations. You require order of n shifting. In case you have to insert the element at any random position, on an average there will be order of n shiftings here. So, order of n time is required for searching and order of n time will be required for shifting of the items as well. We want that these two things should be done together, so that to save some time when we are finding out the position of the element where it should be inserted, along with that you perform the shifting also. So, we should perform the searching and the shifting of the elements hand in hand together. Now, suppose you have to perform the insertion sort of these elements, wherein initially we have considered that the sorted part contains a single element only, that is 80, and we have many elements below this which are unsorted. So, we will pick one element from the unsorted part. Let us say the indexes we have marked here as 1, 2, 3, 4, 5 and 6. We are picking one element from this, that is the second element, this element, and we will try to insert this element in the sorted array. So, obviously the position of the sorted element in the sorted array, 50 should come here and 80 should come below this. So, now this is the sorted part and the unsorted part will now contain the element like this. Now, you pick another element from the sorted part, unsorted part, and insert this in the sorted part. So, 60 should be coming at the place of 80 and consequently 80 will be shifted one step below. So, after this the sorted part will contain these elements 50, 60 and 80, and the unsorted part will contain 30, 40 and 20. And then we have a 30 to be inserted in the unsorted part. So, this should be inserted here. So, when you will insert this 30 in this array, so the elements will be shifted one step down, and sorted array contains 4 elements. However, the unsorted now contains 2 elements only. Pick another element from the unsorted part, that is 40, and insert that in the sorted part. 40 should come at the place of 50. So, the elements 50 onward should be shifted one step down. So, 30, 40, 50, 60 and 80 are the elements in the sorted part now, and the unsorted part contains only a single element. Pick the last element from this unsorted part and insert that in the sorted part. So, since the 20's position should be at the place of 30, so 20 is inserted here, and all other elements will be shifted one step down. So, this is the sorted array. Now, what you have to see here, that here we are performing 1, 2, 3, 4 and 5 insertions. In case we had 6 elements, we are performing 5 insertions. In case we have n elements, we will be performing n minus 1 insertions. If we consider that every insertion is taking place in one iteration, then the total number of iterations that you have to perform here are n minus 1. Now, this is the result of the previous question, wherein you see that the size of the sorted array is growing by 1 in each of the iteration. Now, suppose we have to write the algorithm for this insertion. For writing the algorithm for this insertion, let us consider that we are performing the last iteration only. In the last iteration, let us say this is the element which is required to be inserted. So, let us consider that this element is k. This element needs to be inserted in the upper part. For insertion of this element, you need to make the comparisons and the shiftings. So, let us say we will start the comparison from this place. Okay. So, j is equals to I minus 1. This is the place from which I will be making the comparison. If this element, aj element, will be larger than the k element which is to be inserted, we will shift the jth element one step down. Okay. So, I have compared this like while aj is greater than k element, then I will be shifting this aj element to aj plus 1. Obviously, if this is the 80 and this needs to be shifted down, this should come here. So if this position is 5, this position will be 6. The fifth element needs to be made as sixth element. So that's why aj element has been made as aj plus 1. Once this shifting has done, we will now move to this position, one step back. So that means you need to do j equals to j minus 1, and again the comparison will be made. So if you make a comparison between aj element and the k element, which is 35 here in this case, 60 again is larger than 35, so this will be shifted one step down. So 80 has come here, 60 has come here, and then j will be decremented by 1, j will come here. This element is also larger than the k, that is 35, so this will be shifted one step down. Again j will be decremented by 1, j comes here. Now if 35 is compared with this element is again larger, so this will again be shifted one step down, and j will be decremented by 1. So this is the current position of the j. Now this element 30 is not larger than this k. So in this case, we will say that we have found the position where k should be inserted. This condition has failed, that means the loop has to be terminated. So the loop terminates, and after the termination of the loop, I will insert this k at not j index but j plus 1 index. So k element is getting inserted here, whereas j was here. So aj plus 1 will be equals to this k. Now once this insertion has taken place, let us take one more example wherein this loop condition is not sufficient. For example, you have to insert not 35 but 25. In case you have to insert this 25, then every other thing is fine, but when the comparison is made between this 30 means the first element and 25, this will also be larger than 25. In that case, this element also needs to be shifted one step down, 30 comes here, and then where j is decremented by 1, j comes to the 0 index. Here we are considering that the indexes are starting from 1, it means index number 0 is an invalid index for us. In case we have reached to the invalid index, we cannot go for the comparison. So comparison has to stop here. So in case j is greater than or equal to 1 and aj is greater than k, it means j is greater than or equal to 1 means the comparisons are possible. If j has been reduced to 0, further comparison will not be possible, we will have to stop there. So this is the loop condition where it has to terminate. Let us say j has become 0 and the loop has terminated, j is 0. So in that case also the insertion is required to take place at one index. So that is why aj plus 1 is equals to k, it means a 0 plus 1 is equals to k. Now this is only the last iteration. We have discussed that a total of n minus 1 iterations are required to be performed. So it means that this kind of the operation is required to be performed for n minus 1 time. So let us enclose everything written here in a loop, because every repeated thing should come in the loop. Here we are saying that the loop counter is starting from 1. No, let us take it at 2, because the first element which will be inserted will be the second index element. So the loop counter starts from 2 and it goes up to n, saying that the first element which is required to be inserted is the second index element, and then the third index element will be inserted, and so on and so forth. The last element which will be inserted will be the nth index element. So this completes the insertion sort algorithm. You can see that I have written is afresh. This outer loop is telling you the number of iterations, and this process is telling you that which element to be inserted. Okay. The rest of the things remain same. This actually is telling you the number of iteration, and then this loop is telling you, or this entire thing is telling you, the shifting and placing of item in the sorted array. Now what is the effort required here? Total number of iterations are n minus 1. Let us come back to this problem. In case we are saying that this is the first iteration, the comparison and shifting will require one effort or order of one effort, in the order of 2 for the second, in the order of 3 for the third element's insertion, for the fourth element order of 4. It means the number of comparisons or the effort is increasing in every iteration. Here you can say that the effort in the first iteration, if you count this statement is compulsory, this statement is compulsory, this is a loop wherein we are making this, and finally this. So there are 5 statements which are compulsory here, a 5 statement which is actually required in compulsion for the insertion of the item. So in the first iteration we may require 5, in the second iteration we may require 2 into 5, in the third iteration we may require 3 into 5, and so on so forth. In the n minus first iteration you will require n minus 1 into 5 total effort. If you sum all these, since 5 is common, so you can take it as 5 into 1 plus 2 plus 3 and so on so forth, n minus 1. This is summation n minus 1, which can be written as n into n plus 1 divided by 2. So 5 by 2 into n plus 1. So this is the total effort required. You can write it as 5 by 2 into n square plus n. Here we have a degree 2 polynomial and degree 1 polynomial. We write the complexity with respect to the highest degree polynomial, that is n square. So the complexity of this algorithm will be written in the terms of n square, but we are not decided yet about the notation in which this complexity should be written. Let us take a special case wherein the elements given to you are already sorted. In case the elements given to you are already sorted, in that case when you will compare this element with the above element, this will say that 20 is already at its appropriate position. So you do not need any shifting. Then if you will compare this element with the above element, this also says that element number 30 is already at the right place. Similarly with the 40 is already at the right place, 50 is already at the right place, 60 is already at the right place. So every element which is required to be inserted is already there at the right place. So no need of shiftings. So it means in the comparison, it means this comparison always fails in such situation. Okay, so we have to perform all the iterations, but in every iteration I require only one comparison to be made. Although there are more efforts which are compulsory statements, you can see that there are some of the compulsory statements here. This is compulsory and this is compulsory statement. So that's why I am writing 1 plus 2. So this is required. So 3 effort in every iteration. In case we have n minus 1 iteration, the total effort required is 3 into n minus 1. So this is the best case which can be written in omega notation. So omega n is the best case time complexity, whereas this complexity in which we had to perform all the iterations, and in all the iterations we have gone up to the first position for insertion of the item, will be the worst case, and the worst case time complexity can be written as order of n square. What about the space complexity? Here you can see that you are taking 3 extra variables from your side. One is I, one is j, and another one is k. So 3 are the extra variables that you are taking from your side. So the space function is 3 and space complexity can be written as theta 1. No matter what how big your size of the array is, you will require only these 3 variables and no more. So the best case says that yes, there will be 3 spaces required, so the space complexity will be theta 1. Similar in the worst case also, you require only 3 spaces. So there is only one case for the space, but there are many cases, or there may be more than one case possible for the time. So the time function for the best case would be 3 into n minus 1, which can be written as omega of n. In the worst case, when you have to perform all the iterations, and in each of the iterations the number of comparisons is equal to the number of iteration. So, the total time function here would be 5 into n plus 1, 5 by 2 into n plus 1, n minus 1, not n plus 1, this will be n into n minus 1. So, this will be equals to 5 by 2 into n square by 2 minus n by 2, which can be written as big O n square, because n square is a higher degree term than the n. Now, let us make a comparison between the bubble selection and the insertion sorts. So, first let us see how the bubble sort process goes. In the bubble sort process, we compare the first two elements, and in case the first element is larger, we make an exchange between these two. Here 50 is larger than 30, so we have exchanged them. Then we make a comparison between 50 and 45, since 50 is larger than 45, so they are getting exchanged. Now, we make a comparison between 50 and 10, third and the fourth element. Since this element is larger and this element is smaller, so we exchange them. Now, we make a comparison between 50 and 15. This 50 is larger and 15 is smaller, so we exchange them. And then we make a comparison between 50 and 40. Since this 50 is larger than 40, so we exchange them. Final outcome of the first iteration is this, wherein you fix up the last element, and the last element is the largest one. How many comparisons you have actually made? You have made 1 comparison, 2, 3, 4 and 5 in case you had 6 elements. So, you have made 5 comparisons in case you have 6 elements. In the next iteration, what you will do, you will take 1 less comparison than the previous. So, in the first iteration you have made n minus 1 comparison. Along with this, you have made exchanges, and how many exchanges are there? There are n minus 1 exchanges also, if we assume that exchange took place after every comparison. So, a total of this much effort will be required, n minus 1 exchanges, along with this 3 comparisons, n minus 1 comparisons, and then followed by the exchange. So, in every comparison we are making the exchange. Now, in the second iteration you made 1 less comparison, because you have fixed this element 50. So, you are making the comparison up to only this point. So, 1 less comparison was made in the second iteration. So, the total number of comparisons are n minus 2 into 3. In the next iteration you require even 1 less comparison. So, in the next iteration you require n minus 3 into 3 effort, and so on so forth. In each of the iteration this number of comparison is getting down. In the last iteration you will require only 1 comparison. You can see that you require only 1 comparison to be made. In case you require only 1 comparison, then followed by the exchange, this quantity would be 1 minus 1 into 3. So, the total effort required in the bubble sort process, can be found like a space function and the time function. We have already computed the time function here. Let us sum all these. This is n minus 1 into 3 plus n minus 2 into 3 plus and so on so forth 1 into 3. If you take 3 common here, this will be n minus 1 plus n minus 2 and so on so forth up to 1, and then this quantity can be reversed like this. This is summation n minus 1. The value of summation n minus 1 is n into n minus 1 by 2. So, this is 3 by 2 into n minus 1. So, the time function here is 3 by 2 into n minus 1, or you can write it as 3 by 2 into n square minus n. Hence, the time complexity can be written as order of n square. In the last lecture, we have seen that there is a special case also possible here, wherein the elements are already sorted. In that case, you require very less effort. Now, what is the space function for this? If this is the algorithm for the bubble sort, I, j are the two variables you are taking from your side, and in case you consider that exchange also requires a third variable, so a total of 3 extra variables, extra space is required here. So, the space function is 3 and space complexity can be written as theta 1, because in each of the case you will require only 3 variables and not more than 3 variables. Now, the special case for the bubble sort, in case the elements are already sorted, when you perform the first iteration, no exchange would be required. If you compare the second and the third element, no exchange is required. If you compare the third and the fourth element, no exchange required. If you compared fourth and fifth element, no exchange required. If you compare fifth and the sixth element, no exchange required. So, in case no exchange is required, in the subsequent iterations also there will be no exchange required. So, a total of n minus 1 comparisons took place. You need not do other iterations. You have to stop. You will have to stop the bubble sort here itself, saying that the elements are sorted. No need of performing the future steps. So, n minus 1 comparisons, but no exchange. So, in case no exchange is required, I can write the time complexity as omega n minus 1, and the space complexity remains same. You can see that the algorithm is same only. We haven't made any change in the algorithm. Yes, to stop our algorithm at this point, we need to add extra conditions. Means you can take a flag here. Let's say the flag is 1, saying that the iteration has to be performed. Okay. Now, once you enter this loop, let's make this flag as 0, and the outer loop will run only if, add extra condition here, that I is 1, flag is 1. In case the flag is 1, then only the outer loop will run. It means the outer loop is telling you the iteration. So, outer loop will run only if this flag is 1, and then when the flag is 1, you have entered this, you have made this flag to 0. In case we do not enter the exchange, flag will remain 0 and the outer loop next time will not be performed. So, after the exchange, set this flag to 1, saying that one exchange has taken place. In case no exchange took place, the flag will remain 0 and we will not be coming back to the algorithm, or we will not be performing the next iteration, and we will stop the operation there itself. Now, what about the selection sort process? What happens in the selection sort? You set the first element as minimum, then you find if 30 is less than minimum. Yes, 30 is less than minimum, so minimum is set at this element. Then you find out if 50 is less than minimum, 45 is less than minimum. Obviously 45 is not less than minimum, so minimum will stay here. Next, you compare if this 10 is less than minimum. Yes, this 10 is less than minimum, so minimum comes at the position of 10, and then you compare this 15. 15 is not less than minimum, so it stays here. And then if you compare this 40, this will remain here. What you will do? You will exchange this with the first element. So, this is the first iteration. In the second iteration, you will do similar with the second one. You will find second minimum, then the third minimum, then the fourth minimum, and then the fifth minimum. So, the total effort number of iterations here are n minus 1. In the first iteration, you require n minus 1 comparisons, and after this you need 3 statements for the exchange of the minimum with the first element, and so on and so forth. Here also, if you will compare that, in each of the iterations the comparisons are reducing. If you will sum all these, this will again come out to n square, but since there is no special case for the selection sort, the complexity will always remain as theta of n square. Space complexity will be theta 1, because you require 3 extra variables, for in case 4 extra variable here, because minimum is the extra required here. Now, there is no special case. Let us come to the summary. The bubble sort selection sort, insertion sort, all require theta of n square time in average case. But in case the numbers are sorted, then we get a better time complexity in case of the bubble and the insertion sort, because we can stop our operation early in the bubble sort, and in the insertion sort, even though the iterations are performed n minus 1, but we do not require that much effort, we require less effort. The worst case of these algorithms are big O n square. Space remains the same for all these algorithms, means bubble selection and insertion sorts, they are theta 1. Thank you.